series. Thank you for Professor Arshad, because despite this is a holiday, today's holiday, uh, we can still continue with our agenda. So before I start the webinar, I open the webinar, I would like to read a brief biography from Professor Arshad. So Professor Arshad got his bachelor from Colorado State University in 1986, and he continued to pursue his master in Swansea University and graduated in 1989, and he got his PhD in 1994 from Newcastle upon Tyne University. And for his career, he got his full professor at 2003, and currently he is a director for Institute of Future Energy. Okay, for the webinar rules, I would like to ask the participant to to mute their microphone during the presentation, and you may also want to turn off your webcam. And the second one, if you have question, you may write in chat box, but previously please state your name and institution so I can read where the or whose question is this. Okay, I think that's all for the rules and the introduction for Professor Arshad. The floor is yours, Professor.
Okay, thank you very much, Prof. Rizka. And
sorry, Professor, the sound is too small.
oh, sound is too small. Okay. Is it okay now?
Better, but still small.
Still, make it louder. Make it closer. Okay, Prof. Okay. Is it okay now?
Yes.
Okay. Okay, Bismillahirrahmanirrahim. Alhamdulillahi Rabbil Alamin. Wassalatu wassalamu ala ashrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much, Prof. Rizka and University of Indonesia for inviting me to give this talk. And in the list, I saw also a few names which is very familiar with me, especially those who are considered leaders in the subject matter. Like I saw Prof. Renanto from ITS and few others. So thank you very much. What I would like to do today is basically just fulfill the topic given to me in probably around 40 minutes, I think. 40 minutes, I think, and then, or maybe slightly more than half an hour, and after that we can have a further discussion. Okay. Sorry, just the presentation. Okay. Okay. Okay, the title given to me is basically Process Control and Automation in Chemical Engineering. It is a subject very dear to my heart. I've been dealing with this subject for many years, until something like about probably 15 years ago, when I start to give more of my focus to process safety, because of a few requirements in the country, and we need to have somebody to look into the issue of process safety. And probably, perhaps, when we talk about process safety, the best candidate would come from those with background of process control. For that reason, I volunteered, and we started our program, our master's program on safety. And since then, my research on process control slows down a bit. Nevertheless, the subject is very dear to my heart, and because That's what I've been dealing. I was, in a way, I'm not sure whether the undergraduate student, those who attended this webinar today, what's your feeling about process control? Many students do not like process control actually. But somehow, when I did my undergraduate studies, I like it very much. And that ends me as finally, when I was developing my career, become a professor in process control. So anyway, I've divided my... Sorry, there's a... Okay. I've divided my talk today into 4 parts. The first part is basically talking about, and just a quick overview of process control for the benefit of probably some of the undergraduate students. And then we'll go into the perspective of safety in process automation, control and plant operations. Then we look into the issue of profitability, and then we look into what I think as one, or probably giving some idea what would be a good research topics to go along with regard to, or along with the current technology IR 4.0, and what would be the good future direction of process control research. Okay. Sorry, I got some technical problem, or I need to use assistance now. Okay, next. Okay. Before we move into process control, let's define a process. I think you will be familiar. Process is basically we have input and we have output. Input can be in the form of raw materials, and whatever the output, we can say it is product. To some people it is waste. Waste also have produce. To some people they call it waste, but to some other people we call it byproducts, because anything that comes out of process can be reprocessed and transformed into another form of products. The only difference is that whether it is economical or not. Then there are processes that requires energy, and there are processes that release energy. So we look at a process in a broad example. Okay, in the classroom we look tank, reactor, distillation column as a process. But in reality, a car is a process. Our human body, our body itself is a process. It is consisting of many different unit operation. In fact, our body builds of plants. There are membrane filters like kidneys, and there are pumpings, and there are reactor, and there are all the possible unit operation that we normally found in the process plant. It is basically has its forms in the form within our body. So we can say that our body is also is a process plant, and then oil refinery is another example. Oh, yeah. Let me try. Sorry. Okay. Okay. For example, this is a gas processing plant. Complicated, complex, consisting of many different distillation columns and some other equipments integrated together, and all has to be managed. Okay, and in a typical situation, the process plant basically has many different objectives. The bottom line is money, but at the same time, the plant must protect people. The plant operation must protect people, the workers, the people in the surrounding. The plant operation must protect the environment, the equipment. We don't want the equipment to be damaged, and it must maintain smooth operation. Nobody wants shutdown. One shutdown costs millions for a process plant, and we need to achieve the product rates and the quality. If the quality is not met, you cannot sell your product, and that is a failure. And in order to increase profit, we need to optimize all the first 5 objectives, and then we have the monitoring and diagnosis, trying to identify if there is any rooms for us to improve the process further. These are all achieved through process control. Without process control, we will not be able to achieve this. Somebody may say, in the old days, the plant operates without any of these sophisticated equipment. Yes, but in the very, very old days, the plant may operate, but the controller is basically a human being. It's a manual control. Decision is made by a human, a person. then the manipulation is done by the person, so everything is done by human. Then it gradually replaced by machines, equipment, and today we got so many different digital devices that can be used or that are used to operate process plants. Okay, single loop controller is way back in the old days, and still we have it today. Okay, if you look at one single loop, for example, in the case, this is a case of third tank heater. We have the actuator, which is the valve here, and we have the controller. The controller in the old days, even in today, we can have it in the form of a single loop controller like this. So it's a device. Okay, it's a device that basically, if you look at this particular device, so this is electronic device that has an algorithm wired into it, and then it will determine what will be the suitable valve opening, either fully closed, fully open, 50% open, depending on the difference of temperature measured by the transmitter or the sensor system, with the target value that we set as a set point to the controller. So this is a single loop controller. Okay, and if we look at as the industry gradually grow, okay, then in 1980s the DCS was introduced. Okay, DCS was introduced with the early days. There were plenty of Honeywell, DCS, and Yokogawa mostly. Then there are so many different players come into it. So DCS is basically, we have a system where there is a common shared communication facilities. We call it data highway, and then measurement from process plant. Okay, measurement from process plant collected and transferred into the data highway, and the information is shared to the host computer, where the host computer will be doing all the calculation, and then we have another computer as a storage unit with a different software. For example, there is a software used to be called the one used to be popular, like there is one PhD actually, one called PhD, another one called Pi, which is very popular in those days. But today the scenario is slightly different when cloud computing and remote application is growing. So we will talk about it later. Okay, and then we may have PLC also attached to the system. So this is DCS architecture. Okay, and then after that we have a few other technology developed. Then we have digital technology. As it developed, DCS is transformed in the digital version. This came in the 1990s, first introduced late 1980s, but it was slow until in the 1990s, where the standards were introduced by IEC for functional safety, and for DCS and few other standards were introduced. Then field bus application. By the way, field bus is basically product mostly used, or the name used by the American product. They call it field bus, or we can have some from the European, from German. They call it Prof bus. Essentially, it is the same. Okay, it is basically similar to the DCS. It has the same function, and it has the same shared data highway, but now in the form of digital data. Okay, with high-speed Ethernet, and we can have many different local area networks. So now, basically, if you go to a cyber cafe, we can visualize there is a cluster of computers, maybe wired together as one small network, and another wired together as small network for a large facility. So the process plant may also work that way, where we can have certain area of the plant is basically managed through a local area network, and another one through another local area network, and the networks are connected together, and then sent to the host computer for the overall manipulation or the overall management of the system. So the biggest, I asked one of my friend once. He was developing, basically installing a new field bus system to his plant. He was a plant manager at that time. I asked him, what is your main motivation to replace the old DCS with the current one? Instead of using the normal DCS, now you decided to use the field bus system for his second plant. He was running one plant, so they were doing plant expansion. For the second plant, they are installing a digital field bus system. So interestingly, what he told me that when he did his computing, his calculation on cost, they found a lot of saving on wires and few other things. But a lot of saving on wires, because now we do not need to have so many wires for different measurement, different signals being sent, and so on. Now the wire are all just one computer cable connected to various different devices and go to the computer and so on. And being in that manner, it's easier to isolate the plant, and so it's easier to manage. So this gives an advantage to the process plant on overall management, where it can be a little bit easier to have partial shutdown compared to the old system. Okay, now that's basically the scenario. Today, basically all the new plant, I would say, all the new plant would use a digital DCS or the field bus or Prof bus system. Okay, but we do not want to compare this to some of the small industry where everything's still manual. Even today, there are still some with single loop controller. The single loop controller and the sequence is managed using PLC, and the overall management is done through PC. So PC, PLC, and single loop controller system still exists in the industry today, even till today. Okay, but in the sector like petrochemical, oil and gas, and so on, we are looking at all the new one with digital DCS, like the field bus or Prof bus system. Okay, now let's look at the safety. Let me see, something is missing. It jumps. The slide jumps very quickly to 3 pages. Okay. When we look at the safety perspective, this is what we have, the typical onion kind of drawing, normally found in class lecture notes. In my class lecture notes, I think I found this original diagram. The idea I took was from the website of a Canadian professor by the name of Tom Malin, the author of a book on process control. So I like his presentation, and I use it since then. So at the heart of the system is the basic process control system, BPCS or something, or I put it here as control. So anything on the plant operation, the automation is managing the plant. Okay, so control will be making sure that all the variables, all the process variables is maintained at the desired set points. That's the most important item. We set the set points, pressure, temperature, flow, concentration, and whatever variables that we have for the process plant. For all the equipment, for one plant, maybe we can have maybe 100 or 200 different controllers. So we can have many hundreds of control loops. And these control loops need to be maintained at their desired set point of operation. Okay, that is managed by control. Should the control fail, suddenly somehow, because of non-linearity of the behavior or some disturbances, impact of weather, for example, if some of the pressure loop is very sensitive on weather, if there is typhoon, so it will become very cold, so pressure go a little bit difficult in terms of managing and so on. So then we have alarm system. The purpose of an alarm system is basically to alert the operator, and the operator decides what to do. It is no longer automation. Now it's basically alarm, the annunciator buzz and tell the operator, please do something, we have a problem. Then if the operator fails to put the system on the desired operating condition, now the deviation become larger. For example, pressure was maybe 30 psi at that time. Now it has become 40, and the upper limit, the danger zone is getting closer. So maybe 40 is said to be an interlock system. So where now from controlled by human through alarm, the alarm basically pass automation into human intervention. Now when the operator fails to manage the process, so we go back to the automation. Okay, but now it is no longer in the DCS. It is now on the PLC kind of setup. Okay, where the interlock system trigger do something more drastic, something like shut down certain stream, or shut down certain equipment, or something like that, to relieve the system. Okay, if it fails again, then for thing like pressure vessel, there will be a relief valve, for example, to relieve the system. And the relief system must be fully mechanical, can operate, is not affected by power failure or whatever. So it will be a mechanical device, something like relief valve or rupture disc or something like that. Then the next layer will be containment, basically to prevent the escalation of hazard. Okay, like firewall, bund containment for leakage, blast wall to prevent the blast to exceed certain zone, and so on. So then after that we have the emergency response, where the operators, this is the management procedure to evacuate people. So basically, ideally, in the operation of process plant, what we need is basically control to manage everything perfectly. But we have 6 layers altogether as a protection to make sure that the plant is safe. So if we look at this example which I've shown earlier, let's say we consider a flash separator. Okay, flash separator. In this particular system, we have a flash separator V3. Flash separator, as you all know, is basically just a simple device, just an equipment, a tank, and receive a saturated liquid. And as the saturated liquid is flashes into a bigger volume, so there will be a sudden expansion, and by thermodynamic, reduction in pressure at a constant temperature will cause the vapor to vaporize and the liquid to remain in liquid, the heavier to remain in a liquid. So we have a separation where vapor goes to the top and liquid goes to the bottom, and the separation occur in a single stage. And in fact, if you look at the distillation column, for example, it can be seen, or it can be visualized as a series of many different flash column. Okay, and prior to that, we have 2 heat exchanger, E1 and E2. E1 is basically process-to-process heat exchanger just to recover some heat. E2 is the utility heat exchanger to bring the temperature to the desired set point. So if we look at this particular plant, how many control objectives and how many control loops needed? Okay, come to process control. You know, we are in the academic. Every year we supervise students in plant design. They have studied all the subjects in chemical engineering. Now they are building or designing a process plant. So we look at their control loops that they design. We will find so many loops. So I remember one of my favorite questions to my group would be, can you show me which valve will be damaged first? So the student will say, what? I don't understand your question. So but then normally I will just laugh it out and then let them to figure out later and tell me next week. So basically, naturally, people will think, if we want to maintain the situation under control, have so many different controllers, as many as possible, because the more you control, the better will be the situation, because everything is in place. But in reality, in either to human being or to a process equipment, it is not that way. Normally, the best number of control loops required will be the minimum number of control loops enough to bring it to the desired operating condition. So that means that we do not want to have so many different control loops. We would like to have less control loop, but the number of control loops is good enough such that we can manage the process efficiently. So we have the process, or we as a human, okay, the process can have some rooms for errors, some rooms for maneuvering, some rooms for adjustment, some breathing space, something like that. So for that reason, we will have minimum number of control. So how many for this particular one? Okay, this just as a case study. Okay, now we look at this, oops, they jumped twice. No. Huh?
Left and right.
Okay. Now this is, we look at this particular controller, okay. Normally we need to maintain the flow or the capacity or the flow rate of this particular system. Normally flow will be managed by the most dominant variables. Sometimes it is heating, sometimes it is cooling, but most of the time it is flow rate. So in this example, for example, I put a controller somewhere near V11, so FC over there at the top. But in the reality, in the process industry, normally this is not available to be manipulated because this has been manipulated by the equipment prior to it. So we do not have to fix or to set the throughput or the flow rate because the flow rate has been set for us by the previous equipment. That's normally the case. Then we need to manage the major equipment that can cause difficulty or safety issues or large operability issues. That is V3. So we know that this is a vapor-liquid equilibrium system, vapor-liquid, so we have pressure issue and we have also the liquid level issue. So those are two inventory variables that we need to maintain in order to maintain stability of the process. So we have pressure controller at the top and level controller at the bottom. Then we need to set the product quality, and the product quality is set in this particular simple case using a temperature controller at the feet. So this is this set us with normally just a 3 controller, 1 temperature controller and 1 level controller and 1 pressure controller. Okay. Oh, now it's working. Okay. Alarm. Where do we put the alarm? We have the low level alarm to protect at the bottom to protect the pump from running dry, and we have the high level alarm at the bottom there to prevent column flooding, and we have the high pressure alarm high PAH at the top there in order to avoid or to trigger or to alert the operator to take some action because pressure is increasing and the controller has failed to put it in the right operating range. Okay, so then we have these 3 things, and I'm trying to figure out what disturbed the cursor. Probably because when somebody is coming in, my cursor doesn't work anymore. Okay, so I'm sorry for that. So that's the alarm. And at the next level, we have interlock. An example of safety interlock in this particular case, when the level is so low and it has reached a danger zone for the equipment in order to protect pumps. So we put a level switch low level switch, and that will basically stop the pump from operating. So this is an example of interlock. Then we have a relief system. In this particular case, we have an example of pressure. So if the pressure is excessive after the interlock even cannot be managed, then we have relief valve to reduce or to prevent the pressure from going excessive and causing potential damage to the system or even to potential hazard to the plant as a whole. So that's basically the layer of protection that's available in terms of automation, which is control. alarm, and then interlock, and then relief. The rest is basically management. Is a fixed asset, static devices like burn, containment, and shower system, dispersion prevention devices, and so on, like blast wall, firewall, all those things. Okay, and then evacuation as a management requirement to complete the 6th layer of protection. Now, the current requirement in the process industry is that after the standards of process control was finalized in the 1990s, so finally the industry is basically working on 2 redundant systems. One is managed through a DCS system, which is basically handles all the controls and alarms, and another one which is a system which is redundant operated, ideally with a separate power unit, with a separate backup system for it. The UPS for DCS and the UPS for SIS should be separate. When we do hazard study, for example, for a plant, we need to make sure that we have a complete redundancy. The system must be completely independent from each other. It has to use a different power supply, and even the backup power supply for the interlock system and the DCS should be different. So the interlock system is basically a PLC function, okay, that handles the interlock, partial shutdown and full shutdown, emergency shutdown, and the alarm associated with the interlock, associated with the safety features. Okay, so finally that's the final setup, which is normally the case, is being used in the industry. Now, for part 3, let me check time. Okay, it's about half an hour now. Okay, process operation and control and profitability perspectives. Okay, we look at the profitability perspective. Basically, a 1% saving or 1% improvement of performance is not a small number. A 0.5% improvement is also not a small number when we talk about refinery, because refinery is not an easy industry. The profit margin is not very big. Okay, the profit margin is not very big. The oil price, the raw material price fluctuates significantly, and the product price also fluctuates, and these two fluctuations somehow makes the oil refinery difficult in terms of profitability. We may have a lot higher profitability margin if our operation is way downstream. As we move towards downstream, the profitability margin will be much better, because the product is generally more expensive compared to the raw material, and the amount normally will be smaller. But this is in the case of the bulk chemical processing, like if you have a cracker, for example, naphtha cracker or gas cracker, and if you have a refinery, for example, the profit margin is not very big, but small percentage is a huge amount of money, because the amount is large, the throughput is large. And because of that, if we go around the industry, when we talk about optimization, which industry applies optimization first? We will find out in any country that we go, the answer will be a refinery and a cracker. That will be the two most common industry that is fully automated, with advanced feature, and with a real-time optimization. So when we look at this particular hierarchy, at the bottommost we have the process, we have what we were talking about just now, basic process control system, all the control loops. Then at the higher hierarchy we have the advanced process control. The industry people like to call it APC, but we in the academic, we have different names. We have generalized predictive control, we have model predictive control, dynamic matrix control, we can have adaptive optimization system, and there are many different names that we use in terms of algorithm. But generally in the industry, they just call it APC. What is the APC? They call it, okay, we use RMPCT, the Honeywell product, or we use Aspen product of the particular one, or we use Siemens. So that's normally the kind of language or terminology that used in the industry. We just call it APC. So I put it as APC. So advanced process control. So it coordinates for better control performance. I will dwell slightly detail on this slightly later. Then we have on the top is real-time optimization. The purpose of real-time optimization is moving from one place to a place. I will also explain slightly later. And at the topmost is the production planning. In the old days, in the 1990s, these are not connected. This is just manual department, manual task. Production planning is done separate in a separate department, and then the requirement or the production rates and so on is set by them, and then the plant operation people operates the DCS based on the requirements set by the production planning. Today, a lot of system has been integrated where planning and operation is integrated together. Okay, look at the operating window. When we want to talk about optimization, we look at operating window. Consider this simplified one. The real operating window is multi-dimension. So I have only 2 dimensions in my drawing. So just imagine that we have, for example, pump capacity is one of the constraints. Heating capacity is another constraint. Maximum pressure is another constraint. Maximum temperature is another constraint, and many other variables that I put as a question mark. So there are many possible constraints set by maybe equipment limit. If you go beyond this, we may have basically it cannot deliver anymore. It has reached the limit of the equipment, or sometimes it may be a limit of the process. If you go higher temperature than this, we may get runaway reaction. So it's very hazardous condition. So a combination of process constraint and equipment constraints set the operating window. And the optimum condition that I put as a pink bubble within the area there, that's probably the current optimum operating condition. At that current optimum operating condition, it has a set of set points. What is the pressure, what is the temperature, what is the volume, what is the liquid level for this equipment, for that equipment, and for many other equipment, depending on how large is the scope of the optimization. Okay, if the scope of optimization is 1 unit, then the number of variables will be less. If the scope of optimization is the whole plant, then the number of variables involved will be very large. So that depends on the scale of implementation that used in the industry. So in one situation, the pink bubble may be located there, the best optimum condition or the optimum operating condition. In another hour, maybe because of the situation, the certain situation happen in the processing or some changes in the operating condition and so on, the optimum condition may no longer be there. Okay, so it may need to be shifted somewhere else, maybe a little bit to the bottom, maybe a little bit to the top. So every few hours, let's say 4 hours, 6 hours or so, so we may have different optimum point. And if we have a system which if you have a system which is allow us to run the optimization, real-time optimization the system, then we can change the set points and effectively we are shifting the pink bubble from one place to another. Okay, now the real-time optimization actually, when we look at the situation, is basically if we implement the real-time optimization, if you go from in this diagram from the left-hand side, I had trouble trying to use the cursor here because we tested the cursor cannot be visualized. So you look at the left-hand side. The first time we implement the real-time optimization, we get on the left. Left-hand side. Over there. Okay, over there. Left-hand side, there is a potential profit that we can increase over there, but there is a problem. Okay, so we implement the real-time optimization. The set point change, so the profit increase a bit. Then in few more hours, we implement another time, and then something bad happened to the system. There's major disruption of the process, so we need to adjust. So we adjust again for the third time and the fourth time. So by doing so, we need to maintain. We are able to maintain an average operating condition at some certain level of optimum condition. It may not be perfect, but it will be a lot better than not doing anything about it. So this is a system, real-time optimization. It's not expensive because it is just a software, but the requirement in order for us to do real-time optimization, control must be perfect first. So that's why if we do optimization, because when we optimize, we need to bring the operating condition close to constraints. If we violate constraint, then we are heading for disaster. So we cannot operate near constraints if our controller cannot be behaving very well with a small deviation from the set points. Because we need to realize controllers does not work in a straight line. It is always wavy, and it is always fluctuates around the set points. Okay, but in a typical normal straightforward PID controller, for example, the fluctuation may be larger. If we can improve it by using advanced control like model predictive control, for example, then the variation will be smaller. Then we are now confident to operate closer to constraint and therefore increase the profit. So that's why if we want to do the real-time optimization, first we need to make sure all our control loops are good so that we can operate near constraint. Otherwise, we run optimization, the software set a new set point, and the plant trip. So then we lost money. In fact, we had some experience in the past with the industry that I was working with. We wanted to implement real-time optimization to a refinery, and then during the process, when we evaluate the control loops and so on, then we decided now for this particular phase, we have to build the APC first. Then once we complete all the control issues, then only we can go next level and install the software. And that took few years, I think, three years probably, before we can ascertain that all are okay, and before everybody is confident with at that time we were using RMPCT, the Honeywell model predictive control. Then after having that confidence, then only they went for the real-time optimization, RT-opt. Okay, then model predictive control. So this is a subject of anybody doing research. It is generic. There are so many different names. I remember when I started doing this in 1980s. Okay, reading about it, don't quite understand. But then in the late 1990s, when I did my PhDs, then I started to study very deep into model predictive control. Then, actually, in the end, all those jargons, all those different names, basically can be summarized into something like this. There is a model, there is a process input, the model predicts the future value of the input, of the outputs, and we have measurement, the current outputs, and then we can also predict the future inputs, and based on that prediction horizon, the input horizon and the output horizon, the predicted future input and future output horizon, both the control and prediction horizon. Okay, based on that horizon, then we can define our different controllers. So there are so many different topics in the research in process control, in model predictive control, for example, with different names. Basically, improving certain aspect of this. Some improves how to switch between a certain kind of trajectory into a different kind of trajectory. In certain research, people say, what if I use many different models rather than a single model in order to represent non-linearity? Because non-linear model is not very easy to develop when it is large, when there are so many different variables, and especially if the variables are conflicting with one another, so it's kind of difficult. So they come up with an idea, okay, we'll do multi-model system. Some say that, okay, if we have many different linear models, So, and we put them in a certain structure, they can actually represent a non-linear model. So all those modifications, which is published as different names of controllers and so on, essentially is, in terms of concept, is just similar to what I've been talking on model predictive control. Basically, we predict the future behavior using certain kind of model, and we measure the actual behavior, and we compute the discrepancy between the expected future behavior and the expected and the current behavior, and based on that, we compute and develop certain kind of algorithm that is most effective, most efficient in computing the inputs, and we adjust the input. We can also develop algorithm to effectively adjust the inputs or the control or the manipulated variables so that the implementation become more efficient. So those are basically the subject of research. Okay, but to the practitioner, they don't deal with all these details. They know that they need to develop the model, and the difficult part for the practitioner in implementing this advanced control system is to develop the model. Because to develop the model in the industry, if you use a step test kind of approach, which is normally preferred, that means that the plant has to be put on manual, and you do a step test and observe, and then adjust a little bit. If there is you see that it is dangerous, you take some action. This makes the plant operator very nervous. In the experience of implementing advanced process control in the industry, it makes very nervous. So I remember there was one particular plant wanted to implement APC. So prior to implementing the advanced control strategy in the plant, I was invited to give a week of training to the engineers, plant operators, and so on, to explain to them clearly what is the benefit of advanced control. Because when you implement APC, the return on investment that is achieved will be less than 6 months normally. One plant achieved in 3 months, but normally within 6 months the return on investment can be achieved, but the price is sleepless night during the project, and the price also is we will need some engineer who has to read books, articles in addition to working in the plant. So one time I met one advanced control engineer in the industry, and I asked him, what is your biggest challenge in being the advanced control engineer? He said, people thought that I didn't have a job to do, a work to do, because I was sitting on my desk doing some calculation. So the impression as if he has nothing to do, but he was actually busy working. So that's one of the challenge. Okay, anyway, so much of that story. So the future direction, this is basically what I think. You may disagree, okay, you may disagree, because my thinking may not be the same as your thinking. The Industrial Revolution 4.0 will change the world, definitely. It has changed the world, the way our children is thinking, the way the little kids today thinking, and the way they how they can know about so many different information through YouTube, through reading and so on very quickly. They tend to know a lot of things. A young patient in the hospital were listening to the doctor speaking to another doctor, overheard of the terms. He quickly Googled and found, oh my God, I'm going to be operated in this manner. So he got scared. So that's a challenge in today's world. So similarly, in the process industry, a lot of changes will also occur. And the keywords, if I were to put some keywords in terms of what I think future technology that will be developing today and tomorrow, okay, first is big data. There are so many facility development in big data. Second is wireless. Wireless technology has improved and has enhanced so significantly that we cannot imagine it can be done today. The third is autonomous. Nobody ever thought that one day 10 years ago, maybe 20 years ago, nobody even think of this. But today, we can be thinking, maybe one day I go to a meeting, driving my car, and then maybe one day I will tell, okay, car, you go home, and I want to go home with my friend. So the car will drive by itself going home. It is capable in terms of having the technology today, but it is not implemented because it will create a lot of issues, and the issue cannot be solved today. But who knows? 5 years down the line, probably there will be some regulation, some other facility, some other features that will enable such implementation occur. So, and another keyword that is important for us to visualize when we talk about the future technology is simultaneous. The power of computing facility today and parallel computing has allowed large tasks be processed simultaneously. So if we combine this together, big data, simultaneous, autonomous, and wireless, and maybe there are another bubbles, another ball, number 5, number 6, number 7, if we can add, but I just focus on these 4. Okay, based on these 4, if we were to imagine what can be done, there are so many different things that can be done actually. Okay, I will just give some examples based on simple thing that is practical for us, at least in this particular region, to work with the industry. Okay, first is, okay, is it? Okay, correct. Okay, before I mention some of the thing, the important observation, that is the arrow there. Okay, arrow. That means that if we look at how a new technology is implemented, we in the process industry is the laggard. Process industry is normally lagging behind. We are the laggard. Okay. Normally, new technology will be implemented in military and aerospace. Military because probably the military has some kind of immunity if they have some mishaps, some mistakes. People don't talk about it. Even if they implement something, people got killed. It's for the purpose of national security. So people accepted it very well. So they can do things and try technology quicker than what we do in the normal process industry. Then consumer product, because consumer product normally cheap, small. That's why we see when you talk about pattern recognition, for example, or autonomous operation. Okay, now we can have a robot for vacuum cleaner. So autonomous system for cleaning the floor. The military can have drones to fight the war now with drones. Manufacturing, we are not yet go to that fully autonomous yet, but at least there are so many robots in the manufacturing part. But when it comes to process industry, it is still heavily on human, heavily on the 7 layers of safety protection and the 6 layers of safety and 5 layers of that automation. Okay, still behind. Why? Number one, because the cost of error could be huge. Just imagine one small mistake cause a shutdown of a plant will means that the plant need to be rejuvenate again before starting up. So the shutdown process, they will have to do a lot of things, and then the first product will only come out maybe after a few days if the plant is large, or maybe a week. So all in all, one shutdown will cost several millions. Okay, several millions, $millions, not rupiah, $7 million. Okay, so it's expensive, and plus, if we go around the industry, we can still see the industry operating with control system that was installed in the 1990s, and they're still happy. It is working. So as they say, if it's not broken, why fix it? So it works well, and it can still produce product. Those who wants to go into the higher end, the new technology would be those who are large in terms of capacity. So again, it will be refineries and those kind of industry with large capacity, or process with a very refined, very stringent product specification, maybe pharmaceutical, that may go into in that manner. So okay, one example of research theme that we may look is the sensor technology, soft sensor technology. So because now we have faster computer and with big data capability, we can provide many better estimations. So there are so many different approaches that we can do through either model, statistical model, or artificial, various different paradigm or framework of AI can be implemented in soft sensor technology. Okay, in the 1990s we had an argument about this, whether you want to have online analyzer or a sensor. That was 1990s, but today I believe people are very confident with the soft sensor technology. Then again, as life goes on, the old thing that we enjoy, we never throw it away. So we tend to refine the existing model-based control strategy. So even in 2020, 2021, we see publication in MPC, many different things of many different way, how to improve it further, how to make the model easier to fit for the industry. So that means that using less number of variables, how to make it is more accurate and so on. So this can also be researched. And another interesting topic will be reinforced learning. Okay, reinforced learning can be seen in many different ways because it is a broad subject. Okay, when we talk about reinforced learning, people talk about dynamic programming, Monte Carlo simulation, and few other different methods. How can we adjust? And there are many approach of reinforcement learning. It can also be visualized as in dynamic programming as fitting the model online and improving the model and let the model learn about the behavior and adjust itself along the way. In the past, it was not possible to do so because of computing limitation. Today, because of the power of computing, this has become slightly easier. So we see quite a lot of publication on reinforced learning these days. Okay. Then, man-machine interface. Okay, the last topic that I want to talk about is man-machine interface. This is a very interesting subject. In the 1990s, when I started doing research in process control, there was a lot of man-machine interface research at that time. There was in Purdue and there was in Lehigh University in the US talking about what's the best color for alarm, the sound of alarm, what kind of diagram that is suitable that can make the operator alert but not so crowded and things like that. Today, when I talk man-machine interface, it means more than that. The interaction between machine and man. For example, man can override the machine. That's normally the case. Okay, you have an interlock, and somebody with a key given by the management. Okay, turn on the key. We can override this interlock because this interlock can cause expected damage. We better loosen it up a bit, and we adjust. So that can be done. Okay, people can adjust the set points. The controller work at certain set point. So we want to beat the controller. Oh, go faster. So I cannot make it faster because the algorithm is fixed. So in order to make it faster, so I just increase the set point higher. So it goes a bit faster. Then I will reduce the set point lower again, so that it becomes normal again. So I got a faster response by basically cheating the machine. Cheating the machine by putting a higher set point, which I do not want actually. I want a lower one. So that's one direction. In another direction, which is interesting, there was some research a few years ago. There was a presentation that I listened to in a conference in Prague at the time, delivered by Indian professor. Okay, he was doing research in looking at the eye of plant operator. Looking at the eye, so there are many different cameras just following the eye of the operator, so that they want to know to study the behavior of the operator, whether the operator is in the right right set of mind to make critical decisions. For example, if the operator want to override something and take action, or the operator want to take a drastic action during the alarm period or the alarm time. So if the machine, if the algorithm, if the computing system agree or decided that the operator is not in the right frame of mind, or he is not making the right decision, he can override it. So this require us being observed all the time. So it will be in a way infringement of human rights if you look from that perspective. But things are becoming common, because wherever we go now, even if we go to certain buildings, in the certain high-tech building, if we go moving towards the elevator, before we press the button, the elevator will already know who we are and which floor we normally go. So this direction of technology with plant operation will enable us to strike a balance between human dependent and machine dependent, and we can avoid the human unreliability when it is subjected to issues, problem, and so on, by putting the monotonous action by machine. So the balance between the two probably can be studied as an interesting topic for future. Okay, and as my final note, which is very interesting to me at least, if we study the theory and practice gap, so we always talk about the theory and practice need to be interacted because they are related to one another. But if we look at process control in the process industry, the theory practice gap, in the 1980s, we already have the model predictive control published and tested on simulation basis, understood, refined. Okay, the DCS was introduced in 1980s, but in terms of implementation, most of the DCS came in the early 1990s. In Malaysia, is more of mid 1990s where DCS start to be popular within the petrochemical industry. Then MPC, DCS all introduced in 1980s. Then we have fault detection and diagnosis in the 1990s, real-time optimization in 1990s. But MPC come to the industry in the 1990s. So there was a lag of about almost 10 years lagging. Okay, and then at that time the technology was matured, and the gap in the 1990s and in the year around 2000, 2005, the gap between the theory and practice is quite close. We do research in model predictive control, and the industry also talking about model predictive control. We talk about how to develop the model. They also talk the problems in the model. So we can get along very well in terms of discussing our current research finding with the industry, and the industry can understand our current research finding quite well. I remember this in 2005, if I'm not mistaken, we attended the Advanced Process Control User Forum, where the participants are mostly from industry, except one or two people from the academic, including me. Okay, when I talk about the research that we were doing at that time, and the research is appreciated because they can understand, they can relate to what they need and what they are doing. And as we go on, 2010, 2015, 2020, okay, the development of computing has made our research become very deep into algorithm with large-scale data and so on. So the gap between our current technology implemented in the industry and the current research work that we do in the academic is becoming larger again. So we have this widening theory-practice gap. So this is an interesting observation, at least for the process industry, because in some other industry they can adapt very quickly with the current technology and make use of it quicker compared to us, because we tend to be lagger. So finally, as a conclusion, so I already took about 1 hour now, about 1 hour for my talk now. I'm sorry for this slide extended. Kind of difficult because there's nobody in front to tell me what time is it. Okay, sorry for that. So as a conclusion, okay, number one, advances in ICT will expedite changes in the process control technology. So we will see a lot more new products which is more advanced in terms of technology. However, the process industry is considered conservative because changes require big investment, and if failure costs a lot of money and even can cause a lot of damage. Imagine if it explodes, it costs a lot of, basically it can cause bankruptcy because of the following liability to the environment, to people's life and so on, can be very large. And because of that, the process industry is normally conservative. So, and the current state of the art is considered still profitable enough. And because of that, the gap between theory and practice is currently widening, and in the near future it will be wider again, even wider. But who knows, 5 to 10 years later, there will be something more abrupt happen, and then new technology will be implemented, and probably a new form of process plant will emerge. That will be for us to wait and see. So basically, that's we can imagine what we expect to happen in the future, but we do not know. But I personally anticipate there will be changes, and the change will be faster than the changes that we have gone through in the past. We are lagging behind, but as people moving forward, the process industry will also moving forward, although at a slower pace. So there will be changes, and we need to be able to adjust with the changes and take opportunity with the changes and work accordingly. So ladies and gentlemen, bapak-bapak, ibu-ibu, adik-adik, anak-anak sekalian, thank you for your invitation again to University of Indonesia for me to deliver a topic which I has left aside for a while, but currently working, because now I have one graduate student working on process control after a few years of focusing on energy and safety only. So now we'll start to work on process control again. So if you have any question, I will be glad to answer if I can. Otherwise, probably some other participant, which I believe far more knowledgeable than me. There are many people within the attendees today that can also share his or her opinion. Thank you very much, Prof. Rizka. Okay.
Yeah.
Yeah.
Okay, thank you very much, Professor Arshad. Time flies by. I really enjoyed the presentation very much. It's more than 1 hour, but feels like 30 minutes or less. Okay, now we move to the Q&A session, and several of Professor Arshad colleagues, I believe, asked something. The first question, it comes from Professor Abdul Wahid from UI. So he asked about, in your opinion, what is the best way to student for study process control to suit the industrial needs?
Okay. It is a difficult question, and also can be an easy question, because the industry normally would like us to solve problems in general, except if we are working with the industry where they closely work in the development of process control. Like, for example, Shell, they have the outfit company that basically do research in control. So that kind of industry, with that kind of industry, probably we can go into working into algorithm, working into testing new models, and so on. But if we work with our local industry here in Malaysia or in Indonesia, when talk about process control, actually they are implementing. I believe, I'm not sure the strength of, for example, Pertamina in terms of process control, because I did not engage with them in the past. Okay, but within Petronas, for example, there has been 2 generations of process control engineers now. The senior one has left. Those started in the 1990s has left, go into overall administration, become the big bosses, or went to Doha or somewhere. The younger one emerging. So what they do is basically still the same, trying to implement APC in the plant, depending on projects. So when they implement, the typical problem that they have is always in one is model fitting. How can best we develop a model that to work with the framework of the software that they engage? If they use DMC, so we need to look into how to help them in terms of that. But if you want if we look into something very independent with which is not constrained as far as the hardware is concerned, soft sensor will be an easy working together with the industry, because they always have a lot of variables that still largely dependent on the online analyzer or offline analyzer, and the analysis still introduce lagging in terms of time. So estimator is always the best solution to avoid such a situation. So developing estimators for many different variables required for the industry probably is a viable industry project towards PhD, because we can introduce a lot of new framework of mathematical modeling into the estimator. So that's why I put soft sensor as one of the viable research facility, research topic for us to implement. Otherwise, there are also control problems that relate to specific industry, because there are some specific industry with difficulty in implementing certain problem, especially when the industry is semi-batch. There is batch and there is continuous part. So the transition between batch and continuous, that sort of item also need to be addressed correctly. One example is when we have separation with pressure swing absorption. So there are issues like this, how to improve the efficiency when the process is semi-batch and so on. So that's basically my quick answer to the scenario. But of course, there's always more than that. If the industry is already deep into the matter, I'm not sure, depending on which company that we are dealing with. With some company, probably we can go deeper. With some company, probably it will be more into solving problems. Okay, that probably how I want to answer it.
Okay, thank you. Professor Abdul Wahid, do you want to say something? Pak Wahid, apakah mau berbicara?
Thank you, Prof. Arshad, atas kedatangan di UI ini. Gitu saja. Mungkin yang lain di.
Okay, baik. Okay, we move to the second question. This is from Professor Renanto. So, yeah, he said next presentation, Professor Arshad. So the question is, why do most of undergraduate textbooks in process control only introduce one chapter on process safety? They may have around 20 to 25 chapters, including the MIMO systems. Even the material on process safety does not touch on dynamic aspects on how SIS works. For example, is there any classical textbook on process safety? Or what I think is you may to collaborate to write a good handbook.
Very nice observation. Really. Nice observation. Before I answer that question, let me tell this particular story. Okay, I asked a group of students, why do we learn so much about design and we learn a little only about control? When an engineer graduate, the first place they will be sent will be in the control room. So nobody can answer that question either. So basically, in education, they tend to look at the subject, the courses, as compartments. So we introduce all the theory in hoping that the student get the fundamental. Not only know how to design, how to compute, how tall is the tower and so on, but get the fundamental is more important. For example, the basic thing that any chemical engineer must be good is conservation, and then they need to understand the thermodynamic, vapor equilibrium, then reaction kinetics, and then transport. If they master all the 4 items and they know control, basically they will be a great chemical engineer in the industry. But the way we teach them all the theory to design how tall is the tower, how big is the heat exchanger, and so on. When they work, they don't do that at all. Those who are doing that design is only probably 10% of the population of the graduates. The 90% will be operating process plant. When they operate process plant, they go to the control room and they see what is this PNID. I don't know what the hell is this. Nobody can read PNID. They were lost in the jungle. And we didn't teach PNID. That is a very difficult question to answer, because I was designing curriculum in the old days, okay, when I was younger, okay, and we always thought follow the same trend that the rest of the world is doing, which is basically put it in the compartment. But I believe, like for example, functional safety. Functional safety is something which is very important. For example, now we go to the industry, we look at this particular plant, and we need, for example, the one question that we should be asking, is the plant SEAL certified? And what is SEAL? If you ask any graduate in chemical engineering, generally nobody understands what is safety integrity level. While safety integrity level is one of the core item in process control in the industry, to make sure that the process control system, the process control loop, is certified to provide the necessary risk reduction in terms of safety. But we do not teach. Oh, probably we need a revolution. Very difficult to answer. But I do teach that when I teach the undergraduate process safety class. So I put it in the process safety. So in my process safety class, there is a process control part on it, but in that particular perspective. But now, since I'm normally teaching only graduate student on risk management, so and that related to risk, so it become slightly different. So I believe probably, yeah, Prof Renanto, as your retirement gift to the university, write a book, please. Or we can write together. There is no single very nice book in process safety that can relate to process operation. No single one. In fact, I had the thinking of writing one lately, but I haven't got started. So we always keep on chasing research grant in the energy sector. not enough time to write books. Yeah. Okay.
Okay, Professor Renanto, do you want to say something?
No, thank you. That's a good explanation. Thank you.
Okay. Yeah, you may reach Professor Arshad to write a book then, because he already had an idea to write a book. Okay, the next question is from Professor Muli, I believe, in University of Maluku Saleh in Aceh. I have question regarding the use of big data in Industrial Revolution 4.0 for process industry. Has the researchers and application have been done on process industry, and in what perspective or side of process industry it fits? Thank you.
Okay, to be honest, I do not know exactly what the process industry is doing as far as big data is concerned right now. But I can visualize the starting point where big data will be useful to the process industry will be on the higher end, where we talk about production planning. Now, since the production planning is already integrated with the plant process operation, the production planning where we can include all the scenario, be it economical, social, political, and so on, there will be a lot of complex data. Based on that complexity, the prediction of production rates, for example, can be managed in a better manner. Then we can set the production planning very well. And today, since it is already software, there's already software available to integrate DCS plant operation with production planning. So we can include, for example, consideration of process operation together with political scenario into the planning of production of certain chemical, for example. So I see that as a good starting point, because it will be rather risky going down to the lower level. So if we start from the higher level, probably that's a safer approach. But who knows? Maybe some nice guy one day come with an idea and develop something at the lower end. But the opportunity is there because of the availability of expertise and also availability of facilities. Okay.
Okay, yeah. Prof Muli or Pak Muli, do you want to say something, Pak Muli? Okay, so we move to the next question. This is from Professor Aditya from UPN Veteran Jogja. Thank you very much, Professor Arshad, for your amazing presentation. By considering the conservativeness of process industry towards the advance of technology, so far the education of process control in the undergraduate level, there is no urgency to introduce the student with the advanced process control. Is it correct? Thank you. Typically we use Marlin, but yeah we don't change from 80 something.
Okay. I give my comment, but maybe my comment is not correct. But this is my opinion. Okay. We in the academic, sometimes we are supposed to be the most independent people. Actually, academicians supposed to be the most independent people in terms of thinking, in terms of giving ideas. But within our circle, sometimes we are also trend followers. And we look at the textbook written by the earlier professors in process control, for example. Chapters on advanced control and so on is become a graduate topic. So because of that, we still carry on believing, they should learn it during masters. And we forgot somehow. Why we forgot, I am not sure why. We forgot somehow that most of the people in the industry never do masters. So when are they going to learn about APC, advanced control? So it's kind of a chicken and egg situation. So, but I believe the way we teach process control has to be changed. We should be talking about process control from plant operation perspective first, before we go into start looking into the model and developing transfer function, look at the stability of the transfer function, and then all the tuning algorithm and so on. One day I asked my student, what do you think the best tuning method in the world? So one student say, coherent code. Another one say Google Ziegler-Nichols. Another one say, auto-tuning method. I said, no, it is T&E method. That's the most widely used method in the industry. Trial and error. Because normally, when the plant is constructed, the licensor already set what is the desired operating condition. You already have the set point, and along with it, there is a typical controller setting already been given, set up when the plant is set up. So now what the operator need to do is to tune the controller further. So that is normally done by trial and error. So one day I asked a process engineer, how do you tune the controller? So the process engineer, a chemical engineer, said, I don't know, there was an instrument guy, they come and they look at the screen for a few minutes and then he said it. That's it. So you see these two situations. In the industry, the chemical engineer say, the instrument engineer just fix it. And when you ask the instrument engineer, he does not understand about the process very well. I do not understand really about the dynamic, the transfer function, or whether the response is first order or second order, but he just do it by trial and error. If you want to reduce the fluctuation, you adjust the integral time. If you want to make it slower, you adjust the derivative and so on. So that's what they do. They just adjust the two terms basically. The gain is normally not adjusted unless there is something serious about it. So it's funny, but that's the way we look so far. I tried, I used to teach, I tried once in process control, but it's kind of difficult to change the approach because in our case we have several different sections, several different classes of the same batch. So I teach in a different manner, my colleague teach in the normal traditional manner. So the student got confused. But finally, in the end, we met in the same place. It was okay in the end. But initially, the student get confused because I started with the overall view, system engineering approach, whereby looking at the plant as a whole, plant operation perspective. I took them to the lab to visit the equipment and so on, and then only after that I explained what need to be maintained for this equipment. So a different approach than looking from model, developing a transfer function. So later on we do it. But in our university now, since the last few years, process control is problem-based learning. Nobody teach process control anymore. Nobody teach process control anymore. Just guide the student. It's a problem-based learning. They learn based on the problem given and then guided by supervisors. So that's more or less the situation. I believe the topic of APC, plan optimizer and so on should be included in the undergraduate curriculum. You don't have to study the detailed algorithm, but the student must be introduced to it. The same thing with PNID. The student must be introduced to PNID, how to read PNID in the undergraduate course, and functional safety. They need to understand about functional safety, interlocks, and so on. Somehow, somewhere, either in instrumentation course, or in process control, or in process design, somewhere they need to know at least what is it, so that when they go to the industry, they know what they are talking about. So it's kind of embarrassing when you find your friend from the industry telling, "Hey, how come your student do not know what is what is seal meaning? The meaning of seal? You don't teach them in the classroom or what?" Sometimes we had that and so on. So we end up just joking with the plant engineer, not really answering the question. So okay.
Okay, thank you. Prof Aditya, do you want to add something? Pak Aditya mau menambahkan?
Okay, thank you, Prof, for the answer. Because in my class, usually if we try to introduce first about the process control with the mathematics, they will get confused first. So I think if we can introduce to the student with the real problem in the plant, maybe they will get the insight about the process control, and then we start introduce them with the basic of the process control itself, such as the mathematics and so on. Thank you, Prof.
Yes, actually, I have the experience. You know, in UTM, we have also part-time class in the weekend. In the old days, in the 1990s, I used to teach the part-time class also. And the students are engineer, basically working in the industry. So teaching them process control is a lot easier than teaching the full-time student, while the full-time student has better grades in high school. Academically, the full-time student is a lot better than those who are working rank and file people. They started as a technician and then they become supervisor. So in order for them to become a manager, they need a degree. So they had a 3-year diploma, for example, before that. So they come to our off-campus classes, and when I teach process control, they understand the concept very well, readily, like from first week they already understood. So teaching them become easy. The challenge is only when come to the mathematics, they struggle with the mathematics because they are working people. So probably if we can strike a middle line between the two, will be better for the student.
Okay, thank you. And I also want to add question related to the previous question. Because process control is related also to physics or instrumentation engineering, and also to work, as you mentioned previously, in EPC, maybe we need to design a control, but if we are working in plant, typically we need to do troubleshooting and so on related to the operation. So, in your opinion, until what point should we teach the undergraduate student if we have only one course, process control?
Okay. Actually, our problem is not only process control. Our real problem in undergraduate education is most of our university do not have a course on plant operations. For example, how to troubleshoot when there is a problem in the process plant. Troubleshooting is not taught in the classroom. How to operate startup and shutdown is not taught in classrooms. And how to identify potential problems and things like that are not taught. So if we were to integrate it together, it's quite difficult. In UTM, few years ago we revamped a curriculum, and the curriculum has been running for maybe 2 years by now, 2 years or 3 years by now. We introduced a course called process safety and operability. So in that particular course, actually because I designed the course content, it is somewhat similar to based on the textbook by Marlin a little bit, and some of his graduate courses content also. So when we teach the student about operating window, they need to understand operating window in order for them to understand really how plant operates. And then we teach them about issue of startup, issue of shutdown, and then how to troubleshoot. Even introduce some of the typical method that people in the industry use as a methodology for troubleshoot. And then we teach them process safety. So the way we teach process safety in that manner will be somehow related also to process control, to plant operation. The challenge is not many people willing to teach because it's complicated, complex, and quite difficult. It requires somebody with experience in industry, and I was supposed to be leading the course, but I got so tied up with our graduate classes, so I maintained with for our masters in safety, teaching them. So we groom and train our younger staff to study everything, because they need to have the overall perspective. Design, controls, understanding all the unit operations, reactors. You need to understand everything actually if you talk about operation. And trying to troubleshoot, you have to have example from reactor, examples from separator. So in order to do so, you must understand all the equipment. So those who have been focusing on, for example, thermodynamic only, doesn't want to dwell into reactor design, for example, the problem of runaway reaction. So it's a challenge, but I believe it's important. My suggestion will be, why don't you start that sort of course in the form of elective? Have a try run. Start as in the form of elective. We did that way. It was my elective subject. I used to teach elective subject in plant operation in the 1990s. When I teach it to the off-campus student, they really enjoy it, and we had a fruitful discussion because they brought problems from the industry, and then we discuss. But we need to develop case studies, good case studies, in order to discuss this topic. Okay?
Yes, thank you, Professor Arshad.
I hope I don't get people boring.
Yeah, we'll ask Tawahid then. Okay, I think this is the last question from Professor Hermawan at UPN Jogja. Process control has existed since chemical engineering existed, but unfortunately, students and lecturers are rarely interested. Why is it? And does this also happen at your university?
It's a general phenomenon. A general phenomenon. If you ask in one class, who among you really like process control? I would say maybe 3 people. 3 people or 4. And normally you can see them interact in classrooms. When I used to teach undergraduates, I can identify a few who really enjoys the lecture and who understand. And the rest is basically, I have to make a lot of adjustment in order to make them interested and to make them participate. So in the end, when I teach process control, I ask a lot of questions directly to individuals. So that way, everybody has to be alert and then to stand by to answer to my question. So that's normally I did. So the price that I have to pay is that if this week is the first day of class, next week I lost maybe half of my class. Some new one will come and join me, but half of my class already sign out and sign up with another section. That's the price because they know that, oh, this guy, oh, he asks a lot of questions. So that's the only way to make them interested. But I really believe my experience on showing the scenario in the industry, the equipment, videos, even safety videos, the impact of what's wrong and so on, that will make them understand better. The biggest problem is that if you talk about the first month of process control class, maybe half of the class do not really know what we are talking about and what is the use of this Laplace transform. Maybe we don't need Laplace transform anymore in teaching process control. Maybe. Somehow I think we need a total revamp. Okay? Tapi, but it is a general phenomenon. Don't be sad.
Yeah, it's also the same here. Okay, any other questions? You may raise or unmute yourself. Okay, if not, I would like to thank Professor Arshad for his his great presentation. I believe we all enjoyed the presentation very much, not like our process control class. It's been a pleasure being with all of you today. Thank you. Then with that, I close this guest lecture. Thank you again for Professor Arshad, and I hope to see you again. I hope to see you very soon after this pandemic.
Okay.
Okay. Yeah.
Thank you very much for participants, and thank you to UI for inviting me. Okay. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Prof.
Okay, right.
Okay, the participant may leave the Zoom